Excellent. Well, thank you and good afternoon, everyone. My name is Brandon Royal. I'm a product manager on the Google Cloud team, specifically focusing on GKE and Agentic AI. And we're here to talk about Agentic AI. And I'm sure that's something that hopefully many of you are interested in. We're excited to see a lot of familiar faces here today. Yeah, I guess we'll go ahead and jump right in. And I'm joined, of course, by my partner in crime, Alex Bulankou, who's going to be going through some fun technical demos. We'll make this as fun and interactive as we can, since I heard we are the last session in this room for the day. So hopefully saving the best for last. OK, I just introduced myself, product manager, and Alex is on the engineering side. So I like to start all of my talks with a TLDR. So I'll tell you exactly what you're going to see. And then hopefully we meet your expectations or maybe even exceed them for the next 26 or 7 minutes. So first and foremost, treating agents, we see this, if you look at agentic systems, especially complex agentic systems that use things like code execution, computer use, this is a pretty classic distributed systems problem. So what we'll be talking about is sort of applying a lot of sort of classic distributed systems thinking and techniques to building agentic systems, and how we can actually do that together with Ray and Kubernetes, sort of bringing the best of both ecosystems together to build production-grade agentic AI apps. Ray, of course, this is a Ray conference, so we have to say great things about Ray, and we're actually really excited about all the amazing stuff that Ray provides for agentic workloads. And we'll get into some of the specifics there, but really ideal for agentic tools and agentic orchestration. And then so you bring those two things together, you kind of get the best of both. And then at the very end, we're going to talk about some samples. We're going to go through some cool coding demos, and you'll actually be able to try some of this stuff yourself. OK, what agent presentation isn't complete without defining what an agent is. So we'll, of course, talk about that. When we think about an agent, it's really simple as saying, listen, we have an optimized LLM. It's optimized for tool use. It's optimized for code execution. It's optimized for whatever. Getting it optimized is a process in and of itself. But also, that agent needs to be connected to tools. So we actually think of this as a circular loop. You need to have sort of the agent orchestration that's leveraging the same tools as the system that's building the simulation environment to make your models better. So we think of this as sort of one cohesive kind of system. Again, I'll just re-emphasize the sort of distributed nature of a lot of these agentic systems. There's, of course, your LLM inference server. That has its own scaling properties. There's talks, actually, I'm sure there was at least a half a dozen through the course of the summit, just about scaling inference. Like, that is its own separate scaling concern. If you think about the agent orchestration, like, these are typically your sort of stateful apps. These are the things that are managing your sessions, your users, your context, your history, right? All of that, that's a very stateful system that has its own sort of scaling properties. And then there's your actual tool calling. So how the agent actually calls the various sets of tools, doing those tool calls in parallel, all those things need to sort of happen together. So that's sort of the high-level picture of the distributed system that we think about building for production-level agents. Now, the problems, well, there's lots. The first is around durability. And we've seen this through the course of working with many, many customers who are building these systems for large scale. Maintaining the state for all these tasks, maintaining durability for the task execution, doing these things at scale is pretty challenging, especially when you think about long-running tasks. It's kind of like measuring how great your airplane is by how heavy it is, right? We're talking about how great these agents are by how long-running they are, but it's just sort of a nature of the infrastructure that we have, right? We have to support agents that are running for many minutes, tens of minutes, even hours. And so thinking about building systems that support those applications is important. Isolation, we're going to talk a little bit about what it means for isolation, specifically in the context of code execution and computer use. Sandboxing is something we sort of take for granted, I think, in the industry, but in a lot of ways it's falling short, and we'll talk about some of the things that we're doing to solve that. Scalability, talked about that earlier, right? We need to scale each one of these subsystems independently, and then, of course, efficiency of the underlying compute, particularly for RL. Ray is really a perfect system for a lot of the core logic of agents and tools. The actors are sort of excellent for managing all the stateful bits. Ray actors can be sort of constructed to do that. I'm sure everyone in the room here is familiar with the Ray APIs to make that possible. It's just a very natural fit. And then for all of the sort of tool executions, that's where tasks come in really handy. And you'll see from Alex's demo here that he's going to show you shortly how excellent this sort of pattern works for a lot of agentic apps. But of course, the infrastructure matters, right? And when we're doing this at scale, when we're deploying tens of thousands of agents together with X number of additional tool calls, right? The underlying infrastructure needs to be able to scale so it's durable, it's highly available. And this is really where a lot of customers are turning to Kubernetes, and specifically some of the work that's happening around the interface between Kube and Kubernetes called Kube. So hopefully most of the folks in the room are, hands up if you're using Kube in some way, shape, or form. Okay. Everyone's familiar. I don't have to talk about Kube. Awesome. So it's great. It's the interface that sort of connects Ray and Kubernetes together. So you're sort of familiar with the sort of goodness that comes along with it. Topology bar scheduling. Right, we can make sure the jobs are in the right place. We can get high availability of the control plane. Right, all this stuff sort of works really well. But as I mentioned, there's certain areas where where Ray specifically doesn't fit the bill, and we need to sort of extend or leverage more extensions of Kubernetes. And that's really around that sort of isolation problem I was mentioning before. So if you're doing things like code execution, any sort of computer use, any sort of simulated environments where the LLM is generating something that you need to act upon, running that in a sandbox is sort of table stakes. So hopefully everyone is sort of comfortable with that notion. I don't have to explain why LLM-generated code is dangerous to run in a production system without proper isolation. And there's lots of ways of doing this, right? So hypervisors, micro VMs, gvisor is something that's used extensively within Google to create that sort of isolation between the kernel, the actual host kernel, and whatever's happening within the container. But historically, these sandboxing systems have actually been pretty difficult to scale. This is sort of an infrastructure level concern. And so teams have had to sort of build these sort of custom abstractions. And we've seen like a whole host of startups in the industry that are building sandbox-based APIs and SaaS services. They've been quite successful. So there's a need here, right? We need to make sandboxing essentially easier. And we also need to do this in a way that we don't have to trade off the isolation and protection that we get out of sandboxing with speed and performance that we need for things like code execution. So code execution environments, as you can imagine, we're going to have sub-second latency. We can't wait for multiple seconds in order for our isolation environment, our VM, to spin up. So one of the major areas that we've been working on is a new project called Agent Sandbox. This is officially in Kubernetes open source. It's under Kubernetes SIG. We're going to be talking about it a lot next week at KubeCon. And really the idea of Agent Sandbox is to sort of overlay some isolation or sandbox primitives on top of Kubernetes and really make it sort of perfectly suited for agentic workloads. It delivers things like low latency for sub-second latency for execution using a warm pooling system. If you're deploying this directly within GKE specifically, you'll get the ability to do things like snapshot and restore. So you'll be able to snapshot and restore from a specific pod state. And you'll be able to sort of suspend and resume in order to save compute efficiency. We're also really focused on the developer. So we recognize there's not a whole lot of machine learning engineers that are excited about Kubernetes every day. And that's OK. But we do want to make sure that those teams can access this infrastructure. So we are building things like SDKs and APIs that are specifically designed for clean separation of concern so developers can build on top of these sandboxes. And then this is built in open source. And this is really important to us. Most of our big customers who are building these systems, they need these to be open source. They need to be available so they can see the security principles and sort of primitives, but also that they can integrate them across their cloud environments. So just a quick summary, security, critically important. We talked about really in the context of isolation of agentic workloads. That's one dimension. There are many. Scheduling, of course, is important. We didn't really talk a ton about RL, but as we think about sort of scheduling a lot of those RL jobs, we need to make sure that we're scheduling those efficiently on top of Kubernetes. And then resiliency. We need to make sure these systems are sort of resilient for production. So with that, I'm going to hand it over to Alex to talk about some additional details.
Thank you, Brandon. All right. So Brandon described the individual building blocks. Okay. So to put them together in a production-grade system, we need to answer 3 questions. So question number 1 is resilience. So monolithic agent runtimes create a single point of failure, right? So we need to decouple the stateful agent brain, the reasoning engine, from the stateless ephemeral tools to ensure fault tolerance. So how do we do that? Then the second question is security. So running exec on LLM-generated code in a worker pod would be critical vulnerability. So we don't want to do that. So we need the kernel-level isolation, but provisioning full VMs per task, that would be unacceptable latency, right? And then third, Smart, scalable scheduling. So a simple for loop will fan out a workload and will be a massive bottleneck. So we need to efficiently schedule thousands of dependent tasks across a cluster. We need to manage data locality. We need to avoid serialization overhead. So all of that, all of the three pillars of a production system, and the solution that I'm about to talk about, is designed to answer all those questions. So the solution is what we call the decoupled stack. Directly solve these problems by separating concerns. So the first, Kubernetes is the infrastructure orchestrator. We use it to provision the underlying compute and our security boundaries. So using the Agentic Sandbox CRD, we declaratively define the gvisor sandboxed environments and letting Kubernetes handle the pod lifecycle. Then we have Ray. Ray's application runtime deployed, and we're deploying it with kuberay operator. It solved the scheduling problem. We take a single batch request and fan it out into multiple parallel Ray remote tasks, which Ray scheduler then distributes across the worker group. And then we have the ADK, Agent Development Kit. That's the bridge. It's the client-side abstraction, but that defines our kind of batch-aware tools. I'll describe them, what it means, and make a single HTTP call to the orchestration layer, and then it hides the complex distributed backend. So in the demo that you're about to see, we'll submit a prompt to the ADK agent, which will orchestrate four-phase DAG, or direct cyclical graph, and make 4 API calls to our Ray serve MCP. So the phase 1 is batch fetch. This will call fan out into 50 parallel Ray remote web scraping tasks, 1 for each stock. And then phase 2, that's the batch generate. So this will take a list of references to the data that we scraped in phase 1, and then we'll pass on to the code generation tasks. Then we have phase 3. That's the secure execution. That's the key. That's we have 50 Ray workers dispatch those executions into 50 gvisor sandboxes managed by Agent Sandbox CRD on Kubernetes. And then we have the phase 4, batch analyze. This again will run 50 tasks to aggregate those metrics for each of the stocks. Once everything completes, then will be a single overall aggregation step to summarize everything. All right, so let's go with the demo. All right, so in this demo, which is started to run, I'm going to show you why Ray and Kubernetes is the optimal platform for production agentic workloads. So let me start by launching this prompt in the Agent Development Kit UI. Analyze the top 50 stocks for volatility. So this single prompt launches the concurrent analysis across our distributed infrastructure. So while it's running, let me explain what's happening. So what you see is a 3-layer architecture. So layer 1 is the ADK agent layer. It has batch-aware tools registered. It can understand that it can launch 50 parallel operations with each of those tool calls. It's not a sequential loop for each stock, so it knows that. Then the second layer is the MCP server hosted with Ray serve. And that's the layer that's hosting the batch tools. So we have 50 Ray workers deployed with Ray operator on Kubernetes. And Ray scheduler distributes those tasks optimally across the cluster. That's layer 2. Then we have layer 3. That's our Ray tasks that map to our tools. We have the fetch web data task, generate code task, execute code task, that's the key, that's the sandbox task, and then we have calculate volatility task. Okay? Now, let's look at the Ray serve logs and see what happens. You can see some of those phases already completed, and we can, so the first phase that completed is the fetch batch web data. So it completed across in just 7 seconds. In here, and that's for all 50 stocks. So we launched 50 Ray workers, and each of them fetched data with a different stock. We're using Alpha Vantage API in this demo. And all of this happened in parallel. So 50 workers, 50 concurrent API calls, no sequential bottlenecks. Now, and my smarter colleagues told me I should be using Ray data for more complex data workflows. It has automated batching, intelligent retries, adaptive rate limiting, but maybe an overkill for this one, but that's what we should be using. Now, the second phase that's already completed is generate code task. Similarly, distributed across 50 workers and completed in just under 15 seconds. Now, the most important one, it will execute the third task, will execute the batch Python code. It launched 50 gvisor isolated sandboxes to execute code for each of the stocks. And that's where the power of Kubernetes comes in. So we're dynamically creating 50 isolated execution environments. Kubernetes takes care of everything. Pod scheduling, resource allocation, network setup, security boundaries, all of that is taken care of. And one more thing I wanted to highlight is the data passing model. So the video caption there will say, raise object store, and that's the standard high-performance approach to zero-copy data sharing within an array cluster using in-memory object refs. However, our gvisor sandbox is separate pods. So this makes access to the array object store more complex. So in this demo, I just use cloud storage. Now, array tasks write the results to cloud storage and pass the object key as a reference. The next set of tasks then fetches the data from the cloud storage using that key. Now, cloud storage will introduce latency. That's not something you would use for production. You might use something like more in-memory store like Redis. But my point was to demonstrate that our chained operations don't need to pass the data, only data keys. Now, why Ray? But to summarize again, Ray, smart scalable scheduling, that's the key. And Kubernetes is the foundation of resilient, secure infra. 10+ years now of gold standard of that. And then ADK is the bridge for production agents. You get so much out of the box, like just UI that you saw, that you get with ADK. So all of this powered by Ray distributed computing and Kubernetes orchestration. Now let's go to the next slide. So to recap, so what you saw, and it consistently takes about 3-4 minutes, the workflow executed over 200 Ray tasks total and spun up 50 unique gvisor sandboxes for secure execution. So we had 50 concurrent API calls for web scraping. Before we saw 50 parallel code generations, 50 isolated sandboxes, and so on. And so that's what we mean by decoupled stack. We got massive speed up and parallelism from Ray, and we have solid security and orchestration from Kubernetes. That's how you take your agentic workloads to production. Over back to Brandon.
Excellent, yeah. All right, so maybe just to wrap up here with some key takeaways from the talk, and then we'll answer questions and go into some additional details. So yeah, first and foremost, I mean, hopefully you've seen the sort of power of this combination. Combining Ray, which does an excellent job of orchestrating the sort of stateful and stateless components of task execution and tools with Kubernetes that provides the underlying infra orchestration, but also that sandboxing with Agent Sandbox. And hopefully you've also seen sort of how the pattern can be extended. So this particular example that Alex brought you through was just one of many, right? You can now imagine extending this even further to full agent orchestration. That can all be done within Ray and then extended out through to Kubernetes. And yeah, and hopefully you can also see that sort of power and capability of agent sandboxing, how we can do this at scale. Now, one of the things that we didn't really talk about is like, what are the other capabilities in Agent Sandbox that we're continuing to improve? We talked about latency. One of the things that I don't think you included in the demo was what are the incremental improvements we can get with things like startup latency. So for Agent Sandbox, we're able to get something like 0.7 seconds, 700 milliseconds or so of execution latency. So there's lots and lots of improvements that you can get by leveraging some of the core infra. On the right, you'll see a couple of QR codes. So encourage you to go check out the demo. So the demo repo, everything that Alex went through is available in that repository on the top QR code. If you're interested in Agent Sandbox, you're interested in the open source code, we'll point you to the code repo, but we'd also love to get in touch with you. So this is an open source project. We are sort of working very actively with the community on making it the best project for agent infrastructure. And so we'd really love to work with you, working with partners, not only gvisor that you heard Alex talk about, we're also working in the micro VM system. So working with folks in the Kata container community on things like Firecracker support, QEMU support, and we're sort of looking across the ecosystem to figure out the best ways in which we can provide sandbox infrastructure for all of our users. So get in touch, fill out the information. We'd love to talk to you to collaborate more. And with that, we'll open it up for questions. Thank you all. Yeah, go ahead, in the back.
Thank you very much for the presentation. I wanted to ask you, are you also considering scaling agents? For example, you had just one agent, you were running multiple tasks, but what about if you have multiple requests from different users, for example? Are you also focusing on, we will need to fund new containers that are an agent specifically, but then all the
want to talk about that?
Yeah, we can talk about yeah, so I think we're talking about, the question is, are we considering scaling agents? And that's a very important one, because I think we're talking in this scenario is really the agent is sort of kind of one entity, and then we're really scaling the tool execution inside sandboxes. What about scaling agents? I think it really starts with what's the pattern of how this agent is being used. Are we thinking of an agent as just a server, and at this point we're pretty much launching, or are we thinking of an agent that has a long session, and then we need to really think about how this conversation lasts and how do we manage those sessions. So in many requests, this is the problem that becomes very similar to your typical microservice scaling problem, because stateful microservice scaling problem where you need to maintain the state, initiate multiple conversations. What's important here, though, is that regular scaling metrics, such as memory and CPU, will most likely not quite apply directly. And that's currently we're researching what are the types of metrics. Just like for models, there are types of metrics like queue size. For agents, there will be other types of metrics that we want to use to have Kubernetes auto-scale based on them. And that's exactly what we're researching right now. So stay tuned. I think that very shortly something will come out in open source in Kubernetes where will be guidance about what types of metrics do we use for scaling agents. Question?
Yeah, in the back.
How are you thinking about the reliability of the agent? Let's say the agent dies for certain reasons and you have executed a number of things on behalf of that agent. Like how would it resume from that state that was there before?
Is your question on the agent orchestration side or on the tool execution side, or both?
Actually both.
Okay.
Like how would it persist the state of tool execution and also carry on what it's supposed to do?
Yeah, I'll maybe add something you can add more.
You start, yeah.
So I think for the agent orchestration portion, we're trying to think of these as sort of stateless applications where we're offloading the state into things like memory stores and session stores. So in an ideal world, you should be able to deal with all that just like you would a high available web application. So all the points plus one to what Alex just said, like that's kind of how we're thinking about the resiliency of the orchestration side, which is, I want to say, a more or less solved problem. On the tool calling side, that's when things get a little bit more complex. It sort of depends. There's a cascading problem of like retries and like how that actually gets plumbed back into the context window of your LLM. A lot of that I think can be done through retry logic on the Ray side, and Alex talked a little bit about Ray data and some of the other things that sort of make that part more resilient. But I think that sort of is a case by case, like how you make sure you're doing the right retry logic to ensure that the context you get back in your tool response is sort of clean. Because that's really all that matters over the resiliency of the app. I don't know if there's anything else you would add.
Yeah, maybe to add, when you are running your agent on something like Kubernetes, and with something like Agent Development Kit, ADK, that you can plug in your the storage for your session that's connected to some cloud storage, such as SQL. And that's where, if you say, first of all, you have something where your pod no longer running gets rescheduled, for example, and let's say your agent is doing long workflow, long refactoring, for example. So it's very important that there are checkpoints within that work that the agent is able to come back to. So there are two parts of it. There is a part about kind of memory of the agent. It's the kind of state of mind. That gets automatically persisted, so something like persisted storage service. That's provided by ADK. And then there is a part of the work that it's doing. So usually the work that it's doing, that will be responsibility of your specific workflow to save it. Think of like Cursor, for example, or how those, like they have checkpoints all the way there. So something happens, there is a checkpoint back. So similarly, some of it you get out of the box with integration like ADK. Some of it you'll need to do on your own with implementing based on what your agent is working with. And what's one more important point is that for sandbox that we've been showing here, there is a way to persist the to save and restore the work that happens inside sandbox. This is one of the newer sandbox capabilities that we'll be introducing. So which means that, for example, the work that happens inside sandbox will be similarly persisted and then restored. So basically, it comes down to can be quite complex based on what your agent is doing, but it's definitely something that we have to support for long-running agents.
Yeah, so do you run into any challenges using Ray for, say, like third-party LLM API calls? model-based stuff and what's fundamentally compute-like framework?
Sure, the question was about sort of using Ray with third-party LLMs, if I understand it correctly. So,
yeah, just optimizing for I/O inside, something like Ray or like a Beam-like framework.
I don't know if you have a point of view on that.
No, we can follow. No, I don't have any.
Yeah, I mean, honestly, it's like it should be agnostic. Like at the end of the day, the work that we've sort of shown in the demo was really more around the sort of task management and the code execution. I don't want to oversimplify things, but the OpenAI completions API, it just kind of works with a lot of cases. So we haven't seen like a particular challenge working across different LLMs.
But do you mean like model as a service calls, or do you mean hosted LLMs within the same cluster?
Like the anti-pattern of all of these kind of distributed compute frameworks rely on people serializing something and then instantiating a bunch of workers, and you kind of then end up with this frame passing around callables and having to instantiate clients on stateful actors in weird ways. I found the I/O network calls didn't always play well with Beam or Ray in the same way.
I don't have
it's a good question. It's not something we've run into, honestly. I mean, a lot of the distributed work that we've done with Ray sort of centralizes all the LLM at a stateful point, like with ADK. So maybe there's some ways in which you might need to plumb the LLM from ADK to the particular actor, but each one of the actors they're just stateless tasks that are sort of running predetermined sets of code or task or whatever it happens to be. So not an issue we typically run into. And yeah, go ahead.
Yeah, I'm curious. So do you have a monitoring process for the long run task?
So the question is just about monitoring and just general observability for long-running tasks and agents. Yeah, I mean, this is a huge area of investment that we're doing, and the broad ecosystem is doing it as well. Generally, we're leveraging things like OpenTelemetry as a standard for doing things like tracing and monitoring of long-running tasks. The trick in these distributed system architectures is actually passing the key. So we can do full tracing across, because I want to understand, okay, here's the origin of my requests, here's my session, my user. I then need to distribute that down as a task. I need to run that task in a sandbox. These are all different compute environments that I need to make sure I'm persisting the key. So there's a bit of sort of work that needs to be done in instrumentation. But once you do the instrumentation with something like Hotel, it'll work across basically any system. Google Cloud has a bunch of stuff that's happening there. I don't know how much of it's sort of publicly available, but there's announcements happening this week and next week about some of those agent-specific observability tools. But there's lots of others in the market as well.
As much as we love Ray dashboard is good for maybe real-time playing with it, but for something in production, it probably.
Yeah, it's an observability problem in general.
Yeah.
Yeah, go ahead.
One question: are you planning to put an MCP server around the persistent agent state for context queries?
Interesting.
On the persistent agent state, so around sort of the session management and sort of how we're managing memory, or around the.
On the memory that you're storing, are you planning to put some kind of a front end for other tool calls to query use the MCP server around the memory itself?
You certainly could. I mean, if you look at, again, we'll just use ADK as a sort of reference architecture. A lot of the other frameworks take a similar approach. There are aspects of sort of managing the state of the agent which are outside the bounds of MCP. So things like memory and session persistence, there's session keys, and all the things that Alex was just talking about, and sort of like managing the checkpoints of your data. That's all an AI engineering development problem. Some of the frameworks make that easier, but that's just like straight up, I've developed my app in a specific way. MCP is really about sort of the tool calling that we're enabling. Is it possible to expose that as a tool call? Yeah, I would wonder the use case for that, like what we want the LLM, how we want the LLM to sort of introspect its own memory. That's maybe a philosophical kind of question. I don't really know.
So one pattern is that for something where you interact with this specific agent instance, you're having a conversation with them, that you wouldn't put it into the collective store. But then there is this concept of collective storage across same agent types, where you want to have something persist something which is valuable for other agents. And in that case, that you would expose through your MCP as a tool, and then you have multiple agents talk to that. But you wouldn't put everything there. You wouldn't put the whole session, like Brandon said. For that, you just have your regular session management. But for something that you need persisted, then would go through your MCP.
Can I just on the query that you just executed, will it remember that? And can I later on
Well, not out of the box. You'd need to implement this. Out of the box, something like ADK would give you session storage for that agent instance. It wouldn't be something that other agents would automatically discover. You'd need to implement that yourself, right? Yeah.
But you could certainly implement that. The way that the session stores and the memory stores work, I mean, they're just, they're SQL databases. They're actually really not that sophisticated. So you can figure out how to instantiate memory in all kinds of ways. Cool. All right, thank you very much.